had a gap of a week in between for the lectures of work by energy. Let's start with a quick recap of the concepts we've learned in work energy in the previous two sessions. So we discussed about conservative and non-conservative forces, first of all. So we saw that conservative forces are the ones for which work done is path independent. Okay, and work done in a round trip is zero. Okay, and examples of this include any constant force, spring force, gravitational force, etc. Okay, whereas non-conservative forces these are ones for which the work done is path dependent. Okay, and therefore the work done in a round trip is non-zero. Okay, so the example of this we have seen so far is kinetic friction. Then after this, we discussed about the concept of potential energy for a system. So we saw that potential energy for a system it is defined as the energy associated with the configuration or state of the system. Or configuration of a system. And therefore we saw that change in potential energy is the work done by an external agent to change the system's configuration. If some external agent is changing the configuration of a system, then the amount of work done by that external agent is equal to the change in potential energy. As a result of that work done. Okay, so these are some of the things that we have discussed in the last couple of lectures with examples and things, of course. So we'll continue with examples. So just go through this section once and let me know if there's any confusion about any of the definitions and terms. Then we will come back to numerical examples. Yes, we have seen that example, Tej, of the potential energy of a spring. Correct. We'll look at that in more detail today. All right, now the other thing we'll understand is that if an external agent is doing work to change the configuration only, this much work to change the configuration of the system, okay, that means that the external agent must be doing work against some internal force. Against an internal force, which is resisting that change. Okay, and therefore the work done by the external agent will be negative of the work done by the internal force, which will be equal to the change in potential energy. Okay, and now you can see that since delta U is path independent, okay, because potential energy U is a function or is dependent of the state of the system only. So it's a state function, it's independent of path. Okay. Therefore, this work done by internal force, it must be path independent. Okay. So this shows us that any system that has potential energy, therefore a system can have potential energy only when it has an internal force or forces which is or are conservative, because the work done by the internal forces must be path independent. Okay, and the proper definition of the relationship between the two becomes delta U is negative of work done by internal conservative force. Okay, change in potential energy equals to the negative of work done by the system's internal conservative force. Okay, so this becomes the more broad or more general sort of definition of potential energy. That first of all, when can we define potential energy of a system? We can define it only when the internal force is conservative. Okay, and in that case, the internal force being conservative, to change the configuration of the system, some external agent has to do work against the internal force, which is conservative. So the work done by the external agent against the internal conservative force is nothing but negative of W internal force, which is equal to the change in potential energy. So hence you can see that delta U can be defined in terms of the work done by internal conservative force. So this might be a little confusing first up, but when we understand this with examples, this will become 100% clear. So just make a note of this first. Yeah, I'll explain that with example. It will become clear. See, the idea is if you are having to do work to change the state of the system, that means there must be some internal force you are doing work against. Now, otherwise, how you'll have to do work? If there's no internal force, then there's no need to do work. Now, you can just change the configuration without doing any work. It's only if the system has some internal force, then in order to change the state of the system, we have to go against that internal force. So that's the idea really. Yeah, I'll explain with examples, don't worry. There's no point in repeating the same thing. Just note down this portion first. Yeah, I'll scroll down. Okay, so let us understand this whole concept with a couple of examples. So for example, the case of the spring. Now suppose we have a spring which is initially at natural length. It's an ideal spring at natural length. And now we want to extend the spring. So to change the state of the spring, okay, you can come back later to that. Okay, let's continue with this. Now we want to find out the work done by an external agent, okay, the work done by the spring force, okay, and the change in potential energy of the spring. All these three quantities when the spring is extended from natural length L to an extension. Okay, so first let's see to an extension of D. Okay, or it is compressed by a distance D. So we'll see both these cases. Okay. So see what is happening is in order to extend the spring from its natural length position, we will have to apply some external force like this, which balances the internal spring force. Okay, like this. So if at some point of time the spring is extended by X like this, okay, this external force has to balance the spring force, okay, to keep it in extended state. And the magnitude of that force is Kx. So now you see from here, if we are slightly expanding it further, okay, so we are going from this position to a slight further extension from here. So we made an extra displacement of dx in this direction. So the spring's length is now extended by a further dx. So during that small displacement, dx. What is the work done by the external agent? So for a small displacement, dx, okay, the work done by the external agent will be the magnitude of its force into dx. It will do positive work, so that is kx dx. Whereas the work done by the spring force will be negative of the spring force into dx, because it's acting opposite to the displacement. So it is minus kx dx. And what will be the change in potential energy of the spring? It will be the work done by the external agent, which is equal to negative of the work done by the spring force, because this is the internal conservative force. Okay, so here you can understand, to extend the spring, the external agent is having to do positive work, which is opposite to the negative work that the spring force is doing. So to change the state of the spring, configuration of the spring from x to x plus dx, external agent is having to do plus kx dx amount of work, which is equal to negative of the work done by the internal conservative force, which is negative of minus kx dx. Okay, and that work, which is equal to negative of the work done by the spring force, is stored in the spring as potential energy. That is the change in the potential energy. Okay, but that's happening for that very small change. Okay. No, external force is acting in the direction of displacement, na Tej. So why it will do negative work? अरे work done by force क्या होता है? F dot ds होता है ना. So see, the direction of external force is the same. The angle between them is, yeah, okay. Is the spring force which is doing negative work. You can see that external agent is doing positive work, and that is why the potential energy is increasing. Okay, but at the same time, the internal force, the internal conservative force, which is the spring force, is doing negative work. So that is important to understand over here. Okay, so now for the total displacement from x equal to 0 to x equal to d, extension of d, work done by the external agent will be integration of this. So it will be integration of kx dx from x equal to 0 to x equal to d. So that will become plus half kd square. The work done by the spring, okay, which is basically the work done by the internal conservative force in my system, will be minus of this. Okay, and therefore you can see that the change in potential energy of the spring will be equal to the work done by the external agent, which is equal to negative of the work done by the spring force, which will be equal to plus half kd square. So these are each of these terms. And then we will discuss the second part of the question, where we'll calculate the same things for a compression instead of an extension. Okay, so hope this is clear. Okay, now likewise, if we come to the second part where we are compressing the spring. In the second part, actually not finished. Okay. Okay, finish writing down, Didi. Okay. Now let's come to the second part where next what we are doing is we are, instead of extending the spring, we are compressing it. So in fact, let's do this part now as a numerical problem. So suppose it's given to us that the spring constant, suppose, is 100 newtons per meter. Okay. And it is compressed from natural length to a compression of d equal to, let us say, 2 centimeters. We want to find the work done by the external agent, the work done by the spring force or the internal conservative force, and change in potential energy of the spring. Okay. So to begin with, our spring was having some kind of natural length L, like this. But in order to compress it now, we will have to push it inwards. Okay, so we are applying some external force like this, and all that external force is doing is balancing the spring force, which will this time be outwards. Okay, and because the spring's length is in this diagram, suppose L minus X. Okay, so the external force balances the spring force in magnitude and is equal to Kx. Okay, now from here, if I compress it further by a small displacement of dx, okay, so I'm further compressing it by a small displacement of dx. So again, you can see it is my external force which is doing the positive work. Okay. The internal force is doing negative work, and hence the potential energy of the spring is increasing. Okay. So for the displacement by dx, okay, the spring's compression or the state going from x to x plus dx. So for this change, my corresponding work done by external agent is positive. Okay, work done by the spring force or internal conservative force is minus kx dx. Okay. And therefore the change in potential energy is equal to the work done by external agent, which is the work done against the internal conservative force, and that is positive. Okay, so now for this total change, so for x equal to 0 to x equal to d, that will be this much. So here that will become 1 by 2 into 100 into 0.02 squared. So that will become 0.02 joules. But it will be positive. So this will be 4 into 10 raised power minus 4 into 100 divided by 2. So whereas the work done by the spring force will be minus kx dx integrated. So that will be minus half kd square. So that will come out to be minus 0.02 joules. And hence the change in potential energy as expected will come out to be positive of kd square. So you can see that the spring is symmetrical in both directions. Whether we are taking it from 0 to an extension of d or 0 to a compression of d, in both cases the potential energy of the spring increases. Delta U is positive of this much. Internal conservative force, this term that we use now, this is a short form for work done by the internal conservative force. Okay, so I hope this example is clear to all of you. Now next up, we'll look at a different situation. That's very good. Okay. So in the next example, suppose we are doing something like this, that this height is known to us. Suppose it's 20 meters or something. Okay. Now we take a block of a given mass and we just shift it from position A to position B. By some kind of path. I don't even know what path we take. Some external agent just lifts this block. So a block of mass, let us say 5 kilograms, is lifted from position A and placed at B by an external agent. Okay. Take acceleration due to gravity to be 10 meters per second square. We want to find the work done by the external agent during this process. Okay. Secondly, the work done by gravitational force. Okay. And from that we will see how to define the change in gravitational potential energy. The change in gravitational potential energy during this same process. Okay, so take down the question first, then we'll understand this in detail. Okay. So the first thing that will strike us here is that neither I know the path through which I'm taking the body, nor I know what kind of external force is acting on it. So then how will I calculate? Suppose when the block is over here, some kind of external force like this is acting on it. Okay, and mg is acting on it. Do I know the external force? Do I know the path? Then how will I calculate the work done by the external force? Work done by external force should be integration of F external dot ds from the initial position to final position, but I can't calculate that. I don't know the external force, I don't know Yeah, so I just got disconnected, students. You'll be back online. Yeah, so the problem we were discussing in this question now is that yeah, so the problem in this question is we don't know the external force and we don't know the path. Yes, Tej. You able to understand the question? But then we don't know acceleration also, no? क्या होगा, see, when I lift the block up initially, I must be accelerating it upwards, and after some time, when I place it, before placing it, I must be decelerating it, no? Because it's again at rest. Vashist, very good. We'll discuss. So at A also it is at rest only. Okay. And at B also it is at rest. Okay. So F is equal to ma becomes a bit of a problem. But I have an option that can I use work kinetic energy relation? And the answer to that is yes, I can, because the net work done is equal to work done by the external force plus work done by the gravitational force. Now this is unknown, but this is known because this is a conservative force. And on the other hand, do I know the change in kinetic energy? Yes, because it's at rest. U is equal to 0 at A, and final velocity is also 0 at B. So I know the change in kinetic energy is 0. So I can use the work kinetic energy relation. We're getting the point. So abhi dekho, even though it's difficult to calculate the work done by the external force directly, but the work done by gravity is easy to calculate because gravity is a constant force, so it will only depend on the displacement. So the displacement of the block is some x I cap, but plus h j cap now. You take x and y like this, and mg is minus mg j cap. So it is a force of minus 50 j cap in newtons, and this is some unknown x, but plus 20 j cap in meters. So from this I will see that the work done by gravity is easy to calculate because it's a conservative force. ये कितना हो जाएगा? It will be the dot product of these two. So you see it will become minus mgh, or it will be minus 1000 joules. Okay, that is the work done by the gravitational force here. So very good, Bashish, we have worked this out. Okay, so as a result of that, now I can calculate the work done by the external force also, because the change in kinetic energy is 0. No? So when I apply work kinetic energy theorem, I'll say that okay, net work done is equal to change in kinetic energy. So that is work done by the external force plus work done by gravity is equal to half m 0 square minus 0 square, because u and v are both 0. So work done by the external force minus mgh should be 0. So the work done by the external force is becoming plus mgh, or plus 1000 joules. Whereas already we've seen the second part. So it's like we have to go backwards here. We have to first calculate the work done by gravity, because there's no way we can directly calculate the work done by the external agent, and then use work kinetic energy relation to get this. Okay, and now use the relationship between. So now we take, if we take Earth plus the block as a system. Okay, where basically what happens, the height of the block, that is the state of the system. So whenever the height changes, there is a state change. So change in potential energy of the system will be negative of the work done by gravity. The change in gravitational potential energy will be equal to negative of work done by gravitational force. which is the internal conservative force. The gravitational force is the internal conservative force. So from that we'll get that delta U is also equal to plus 1000 joules. So the third part, delta U, will also come out to be plus 1000 when we connect these two concepts. Okay, but note down the first two parts. So first note down up to this, the work done by gravity, and from that how we calculated the work done by the external agent. Okay, so now let's come to the change in gravitational potential energy. So that will come from here. Right? It will be plus 1000 joules. That becomes the third part of our answer. Okay. Okay, so hope this question is, this example is fully clear now. Okay. So now see what we have established through these two examples, we can generalize for any system now. So just like in the first example, we saw that because the spring has something called the tensile force or the spring force, which is conservative in nature. So that means every time we have to change the state of the spring, we have to do work against that conservative force. And the amount of work done by us against that conservative force will be path independent. It will only depend on state because after all, it is work done by a conservative force. So we can define the spring's potential energy. So like that, when we take a certain block with the earth as part of a system, then whatever interactive force the block is experiencing because of the earth, that gravitational force, it is conservative in nature. That means whenever I want to change the state of the system, that is I want to move the block around, I have to do work as an external agent against the gravitational force, which is conservative. So I have to do a work done which is path independent. So that means I can define potential energy for the system because the internal force is conservative. Tensile force is the same thing as tension, springs tension or tensile force. Okay. So in general, we can say now that any system, for any system having internal conservative force, okay, which we can denote by this symbol, internal conservative force. Okay, potential energy can be defined, or you can say potential energy will be defined is such that the change in potential energy during any change in configuration is equal to negative of the work done by the internal conservative force, or it is minus of F internal conservative dot ds. So this becomes the relationship between internal conservative force and potential energy. So change in the potential energy, okay, during a state change, during a change in the system's state will equal to the negative of work done by the internal conservative force, okay, during that state change. And this is the definition we applied to the two systems that we just saw. In one case, the internal conservative force was the spring force. The other case, the internal conservative force was the gravitational force. So for the spring case, the potential energy was called the spring potential energy, or we also call it the elastic potential energy of the spring because it's related to the property of elasticity. The spring's tension or tensile force comes as a result of elasticity. And in the second case, we call it gravitational potential energy because it comes as a result of gravitational force. Okay. Now, common examples of potential energy. Let's look at them. So, obviously, the most common are the ones we've already seen: the spring potential energy and gravitational potential energy. So, elastic potential energy of a spring, which we can denote with the symbol U of the spring. Okay. So, as we just saw that delta U of the spring is negative of work done by the spring force. Okay. And anytime a spring force is acting like this because the spring is extended and we are displacing this further, or anytime the spring is compressed. Okay, so the spring force is acting like this, okay, and we are compressing it further. Either way, this will be minus of minus kx dx, integrated from whatever the initial position to whatever the final position. Okay. So delta u will be integration of kx dx from initial to final. So that will become half k x final square minus x initial square. Now delta u is nothing but change in potential energy. So delta u can be written as final potential energy minus initial potential energy. That can be written as half k final x square minus half k initial x square. So from that we can define the absolute potential energy. U will become half kx square. So this is how we define the potential energy of a spring as a function of its position. This is the elastic potential energy of the spring, and it is a function of its state. This is nothing but the value of x. Now, whether x is positive or negative, you can see. So you can see that x being positive means that it's in an extended state. X being negative, it's in a compressed state. Okay. But in both cases, the potential energy is positive because there's an x squared term. So the potential energy of the spring versus x has this kind of a graph. From natural length, whether we take it to a positive value of x or we take it to a negative value of x, we have to do positive work on the spring because its potential energy is increasing. So this is the full discussion about the complete expression about the elastic potential energy of a spring. And finally, this formula will be the important thing that we'll be using directly in questions. All right, the second common example we'll be experiencing for potential energy is gravitational potential energy. Okay, I'll wait. Okay, we'll come back to that. Okay, finished writing, Tej. Okay, good. So next, let's come back to gravitational potential energy. So these are the two direct formulae that we'll be using in this particular chapter. In future chapters, we will see more formulae coming in also, like electrostatic potential energy, etc. But currently, these are the two standard formulae you have to remember. The first was the spring potential energy, half kx square. Second will be this. So gravitational potential energy here we'll be defining is a bit specific. We'll define it for a body of mass m, okay, placed at the surface of the earth, okay, or at a height h such that h is very small compared to radius of the earth. This term is radius of earth. It is approximately 6,400 kilometers. Okay. So we are only defining it specifically for this kind of situation. If the height of the body is comparable to the Earth's radius or larger than the Earth's radius, then the formula that we're developing right now will not work because the value of small g will change. So what happens for this constraint that h is small compared to the radius of the Earth is that small g is uniform. Acceleration due to gravity is uniform. Therefore, mg is a constant force, constant or uniform amount of force. Okay. So that's why later when we see the chapter of gravitation, universal gravitation, we will see that the formula changes. Yeah, because the distance from the center of the earth as it changes, I mean from the surface of the earth as it becomes large, then the gravitational pull because of the earth's mass will start to weaken. You're understanding the point? Actually, gravitational force is also an inverse square law type of force, no? Like electrostatic force. So actual gravitational force on a body depends on the distance from the earth's center. So that's why. Anyway, we will be studying that in a future chapter. So here we need not worry about that. So under this constraint, if we take the y-axis as a vertical axis and the x-axis as a horizontal axis, so gravity is acting in this direction, then we can say that delta U is negative of work done by the gravitational force. So that is minus of mg dot displacement. So we take the body from the surface of the earth through any path like we did in that example where the vertical component of its displacement Okay, so the displacement of the body is delta x I cap plus delta y j cap. But while this displacement is happening, the gravitational force acting on it is always minus mg j cap. It's a fixed amount of force. So from this we will see that this becomes minus of minus mg delta y. Sorry, there's no integration here. It's a direct, my mistake. It's a work done by a constant force, no? So it's F dot S. So it is minus of mg dot S. So that will become minus of minus mg delta y. So change in gravitational potential energy will become mg delta y, where delta y is the vertical component of displacement. Okay, and that's why you can understand that if delta y is positive, then gravitational potential energy is increasing. Okay, whereas on the other hand, if delta y is minus of h, we are taking it down through a height of h, then our gravitational potential energy will be decreasing. So anytime you lift a body up to a greater height from the surface of the earth or from its initial height, you're increasing the gravitational potential energy. And every time you allow the body to drop or you bring it down to a lower height, the gravitational potential energy is decreasing for the body. This is the simple rule of thumb to remember. Yeah, Tej, I've explained that over here, that if our vertical coordinate is positive, I mean the change in vertical coordinate is positive, that means we are taking the body to a greater height from its initial height, then gravitational potential energy is having a positive change, that means it's increasing. Whereas if the body is coming down to a lower height from where it started, so delta y is a negative quantity, so then delta u will also be negative. So body that is decreasing in its height will lower its potential energy, and a body whose height is increasing will be increasing its potential energy. This will become very obvious when we apply work energy to a situation like a projectile or a vertically projected object, etc. Okay, so we are coming to that, all that very soon. But before that, let's look at an. So these are the two standard formulae you should know. Okay, for the questions in this chapter, potential energy of the spring is given by the formula half kx square, and change in gravitational potential energy for a body of mass m taken through a vertical displacement of delta y, or vertical component of displacement is mg delta y. These are two standard formulae which we'll be using in questions. Okay. Okay, we'll come back to this. Finish writing this down. Okay. Yeah, so before we come to those sort of examples where we use the standard formulae, let's look at another type of problem where we are given some imaginary type of situation where the conservative force is given to us as a formula, and from that we have to develop the formula of potential energy. Okay, so let's say we have a one dimensional system, or a particle moves along the x-axis such that a conservative force okay given by F is equal to alpha by x square, where alpha is the constant acts on it. Okay, so if alpha is equal to, let us say, 40 Newton meters square, then and its potential energy at x equal to 1 meter is 50 joules. Then find the work done by F for displacement from x equal to 1 to x equal to 5 meters. And second, the change in potential energy delta U for x equal to 1 to x equal to 5. Okay. And a general formula for potential energy as a function of x. Potential energy as a function of its x coordinate. That general formula we have to develop. Okay. So just try out this question. This is just based on the concepts that we have just learned, that delta U for any system is negative of the work done by the internal conservative force. That is negative of F dot ds for the internal conservative force. So this concept here has to be applied. Okay, let's understand. So the first and foremost thing here is you can see that the direction of the force is positive now, because it's alpha is a positive quantity, and you're moving from x equal to 1 to x equal to 5 now. So you're moving in the positive x direction. So how can the work done by the force be negative? Now, the work done by the force has to be a positive quantity. Delta U will be negative. And this only is the internal conservative force now. The force F is only the internal conservative force now. So what's happening is, let's say on this body or block or whatever, the internal conservative force acting is this one now. This alpha by x square, when it is at a position x, this is the conservative force, the internal conservative force. So when this moves from some position A like this to some position B like this, the work done by the internal conservative force is this. So it is alpha by x squared dx from x equal to 1 to x equal to 5. So it is minus alpha by x from x equal to 1 to x equal to 5. So it is minus alpha, or it is alpha into 1 minus 1 by 5. Or in general, if I say that the work done by the internal conservative force is from some initial to some final position. So it is minus alpha 1 upon x final minus 1 upon x initial. This is the general expression for which I have substituted 1 and 5 over here. So this is becoming 40 into 4 by 5. So 160 by 5, or 320. So 32 joules. So positive 30 joules, 32 joules is the work done by the force F. Okay. So this is the work done by the internal conservative force for my system. Okay. From x equal to 1 meter to x equal to 5 meters, because alpha was given to us as 40. Okay. Nee, so that is the thing. It's not saying there's any external force. It's saying that the conservative force is acting on it. So what is the work done by that conservative force? So it is so much. Okay. Now the second thing is that because this force acting is conservative, so we can define potential energy. So the delta U for this system will be negative of the work done by the internal conservative force. So that is negative of work done by this particular force only. Okay. So delta U will be equal to minus 32 joules from x equal to 1 to x equal to 5 meter. This is the next thing. So if the body is going from x equal to 1 to x equal to 5, the change in potential energy of the system, according to the information given to me, is a drop in 32 joules of potential energy. It loses 32 joules of potential energy. Okay, so this is the definition where we're talking about potential energy for the system for which F equal to alpha by x square is the internal conservative force. Okay. And now the third part of the question, you want to find the general formula for potential energy. So we can use this, that delta U is negative of f dx. Okay. Now for this we can take U at some value of x minus U at x equal to 1, because it was given to us that the potential energy at x equal to 1 is, how much was it now, 50 joules. This was given to us that at x equal to 1 the potential energy is 50 joules. So this is given to us as 50 joules. So this should be equal to, on the other side, from x equal to 1 to the general value of x equal to x. So potential energy at x equal to x minus 50 is equal to alpha this. So potential energy at x equal to x will become 50 plus alpha into 1 by x minus 1. So that is 50 plus 40 to 1 by x minus 1. So that is 10 plus 40 by x. So this is the potential energy as a function of x in joules, where x is in meters. So you can see at x equal to 1, the potential energy is equal to 50 joules. At x equal to 5, you can check out the potential energy is 10 plus 40 by 5. So it is 18 joules. So delta U, which is the potential energy at 5 minus potential energy at 1, is 18 minus 50 or minus 32 joules. So it also agrees with the calculation we've done earlier in part 2. See, that will be clear, Kunal, from the statement of the question. Now, here the question is saying that a conservative force of this much acts on the particle, therefore define its change in potential energy. So obviously we have to consider that conservative force only as our internal conservative force. If that was an external force, then it would have clearly mentioned that an external agent applies a force of so much on it. You're understanding the point? ना, अगर क्वेश्चन का मतलब ये होता है that force of alpha by x square is applied by some external agent, then it would have clearly mentioned that. But here it's saying that it's a conservative force that acts on a particle while it's moving along the x-axis, and it's so much. So if we are defining potential energy for the system, that conservative force only has to be taken as the internal force of the system. Okay. Now, when we discuss work energy theorem, this will become even more clear to you. Okay. That okay. Good, good. Okay, so hope this example is clear. For a situation where if you are just given a conservative force, how you will define the potential energy for that conservative force. So given the formula of the force, you will just use this relationship that delta U is negative of work done by the internal conservative force. So it is negative of F dot ds or whatever that conservative force is given to us. This is the expression. Now coming back to the application of the concept of potential energy. So next we will discuss the most important thing in this chapter, which is called the work energy theorem. So everything that we have learned up to date in this chapter is basically for the sake of application in this theorem. So work energy theorem, you can say it is like a different version of work kinetic energy relation, which we've seen before, but it's a more useful version of that. Okay, so work energy theorem is defined for a system, okay, undergoing in general a change in its state, okay, and or its kinetic energy. So it might be that only the state is changing, the kinetic energy is not changing, or it could be only kinetic energy is changing, its state is not changing, or it could be both are changing. So that's what we mean by saying that undergoing a change in its state and kinetic energy, or its state as well as rather its state or its kinetic energy. Okay, so it is defined for such a system acted upon by some external force, okay, and or some non-conservative force. So under the action of some external force, and along with that there may be some non-conservative force present, or they may not be, whatever be the case, the system is undergoing a change in its state and or its kinetic energy. So for such a situation, we define the work energy theorem, statement of the work energy theorem like this, that the work done by the external agent, okay, plus the work done by the non-conservative forces equals to the change in kinetic energy of the system plus the change in potential energy of the system. Okay. The work done by external agent or external forces plus non-conservative forces, if any, this total equals to the change in what we call the mechanical energy of the system. So the mechanical energy is the sum of kinetic energy and potential energy. So that is the statement of the work energy theorem. So just like we had seen that various types of systems are very convenient to solve by using the work kinetic energy relation, that net work done by all the forces on a body equals to the change in its kinetic energy. Now like that, we'll see that for certain systems, it is even more convenient to use this theorem than the work kinetic energy relation. It's even more convenient to use this theorem, which relates the work done by the external and the non-conservative forces with the mechanical energy of the system, where mechanical energy is the sum of kinetic energy and potential energy. So, I mean, this is the final part of the chapter, and the main applications are going to be based on this theorem. So, also we generally denote the mechanical energy with the symbol E, and that is the sum of kinetic energy plus potential energy. Or you can say that the change in mechanical energy is equal to the change in kinetic energy plus change in potential energy. It's done in theory, like you will take some time to complete all the questions and discuss the various applications. But this is the last additional theory part. Of course, we have to discuss a little bit about power also. but that's a small thing. Conceptual part is done. We have to still put in a few lectures for the applications and discussion of that. Okay, so let's look at a simple example. So suppose we have this situation. There is a block attached to a wall on a rough surface. So this is having a coefficient of friction, and it's attached to this via spring, okay, which is initially the block is at rest, the spring is at natural length. Okay. Now from t equal to 0 onwards, a constant horizontal force is applied by some external agent. So the block of mass, let us say 4 kilograms, attached to an ideal spring of spring constant, let us say 25 newtons per centimeter, is initially at rest on a rough surface. Let's take mu as 0.1 as shown. Okay. Now a constant horizontal force of magnitude, let us say 10 newtons, starts acting on the block. Okay. So find the speed v when x is equal to 2 centimeters. That is the extension of the spring. When the spring is extended by 2 centimeters, then what is the speed of the block? You have to calculate this. Okay, now we will tackle this sum by two methods. One is what we've just learned, work energy theorem. And work energy theorem is always applied for a system. So we will take a system as the block plus the spring. And we'll also tackle it by the earlier method that we used to use in questions like this, which was the work kinetic energy relation. Okay. And that was basically that the net work done by all the forces acting on the block equals to its change in kinetic energy. So this theorem being applied to the block. And we'll understand why this is going to be much more convenient rather than this, because we have a formula for potential energy of the spring. So we have to do less amount of calculation. Okay, now we'll see through this question how exactly work energy theorem can be applied. Okay, so let us first go by the work energy theorem method. Okay. So we are taking our system as the block plus the spring. Okay. So as the block is moving, the system is going from this state to this state. And by now it has some speed v. While the external force, okay, the block is undergoing a displacement of x, and also there is kinetic friction acting on it. Okay. And of course there is mg and normal reaction acting on it. Okay. So you can see that work done by the external force for this system will be F external into x, because F external was a constant force, and that too it was a force of 10 newtons magnitude. Okay. And we want to find out for a displacement of 2 centimeters. So 10 newtons multiplied by, so this is becoming plus 0.2 joules. This is the work done by the external agent, because work done by normal reaction is 0, work done by mg is 0. They are acting perpendicularly, so only the external force is doing work. Work done by non-conservative force over here is the work done by kinetic friction, which will be minus of kinetic friction into s. So that will be minus mu mg into x. Okay. So that will be minus of 0.1 into 40 into 2 into 10 raised to minus 2. So 4 into 0.02, so minus 0.08 joule. This is the work done by non-conservative force. Okay. And the work energy theorem for this system will tell us that work done by external forces plus work done by non-conservative forces should be equal to change in kinetic energy of the block plus change in potential energy of the spring. Okay. So this will become this will become minus mu mg x. This should be equal to half mv square plus half kx square. Because you can see that the initial kinetic energy of the block is 0, because u was 0 initially. The final kinetic energy of the block is half mv square, where v we have to find out at x equal to 2 centimeters. The initial potential energy of the spring was 0, because x was 0 initially. The final potential energy is half kx square, where x is equal to 2 centimeters. Okay. So from this, what we are getting, see, this is plus point, how much was it? 0.2. Yeah, 0.2 joules. Okay. Minus 0.08 joules is equal to half into 4 into v square plus half into k. Now k, remember, was 25 newtons per centimeter. So that is the same thing as 25 into 10 raised power 2 newtons per meter. Okay. So this will become 25 into 10 raised power 2 into x, which is 2 centimeters. So 2 into 10 raised power minus 2 square. So this side we will get 0.12 is equal to 2v square plus, now this term will become how much? This will be 25 by 2 into 4 into 10 raised power minus 4 plus 2. So that is 50 into 10 raised power minus 2. So 0.5. wait a second, we have taken too large a value of spring constant. Spring will actually not allow it to go that far. So we'll reduce the spring constant a little bit. We'll change it to 2.5 newtons per centimeter. Just mark this change, because otherwise the system will actually not be able to go up to 2 centimeters. The external force will not be strong enough for that. So this will become, okay, so 0.05. Okay. So we can see that V square will become in SI unit. So V will become square root of 0.07 by 2, or square root of 3.5 into 10 raised power minus 2 in meters per second. So we will be very nearly square root of 3.5 will be something little bit less than 2, but greater than 1.7. Just check. So 1.87 actually into 10 raised power minus 1 meter per second, or you can say it is about 18.7 centimeters per second. This will be the speed of the block at x equal to 2 centimeters. So this is the application of the work energy theorem. Okay. So make sure you understand this properly, and when you are revising this later, also do this question once yourself by the second method, which is the work kinetic energy relation for the block. So that will tell you that the net work done should be equal to the change in kinetic energy. So the work done by the spring force plus the work done by the friction plus the work done by the external force, this is the net work done. This should be equal to the change in kinetic energy. So using this, you will come to the same conclusion. Okay, but it will be a more complicated process, but because you are separately calculating work done by the spring, whereas here you are using the formula for potential energy of the spring. Here you are using this as a formula, whereas here you are doing the calculation of work done by the spring. So it's one step less. Okay, people, so hope you are clear about this. Yeah, so homework, you can continue doing questions from H.C. Verma, from Work by Energy chapter. And you can do questions up to question number 43. Okay, H.C. Verma, Work by Energy chapter. Actually, it's called Work Energy Theorem chapter. So do up to question 43. Okay. In between, there are 4 or 5 questions which are based on power concept between about 22 and 27. Leave out those questions. But most of the questions are to do with either calculation of work done directly or the application of work energy theorem now, which you can easily understand from this. Okay. So that's it for today's session, people. Wish you all the best.